A second and a very common precursor to alkenes would be alcohols. And in order to get to an alkene from an alcohol, we need to remove formally a molecule of water by removing an OH group from one carbon and a hydrogen from an adjacent carbon. This route is very common, and this is certainly due to the fact that alcohols themselves are very common compounds. They're often encountered in industry and in many routes, and they're very cheap and easily available, and so therefore a lot of alkenes are made from by dehydration of alcohols. Now, dehydration itself means removal of water, and this is an accurate description of a reaction that we're trying to do, where we have an alcohol with hydrogen and OH group attached to it. This will be an alcohol. And upon treatment with acid, what we'll get is water plus an alkene. This reaction is reversible because, as we'll see in next lecture, alkenes can be hydrated to give an alcohol. However, we can do things to push the reaction towards alkenes, and the principal things that we would do is try to remove water or try to distill off the alkene. Typically, alkenes will have a lower boiling point than alcohol because alcohols can hydrogen bond to each other, and therefore alkenes can be selectively removed by distillation from the reactor mixture, which will then push the equilibrium towards creation of more alkene. In order to see how this works mechanistically, we can look at the example of 3-pentanol, shown here, which can be treated with H2SO4 to give us initially the protonated pentanol, and HSO4-. The reason why H2SO4 is often used in this reaction is because HSO4- is not a good nucleophile. If you try to think what would happen if we used a different strong acid like HCl or HBr, what we would get is a protonated alcohol, but then the other thing we would get would be Br or Cl-, which are good nucleophiles, and then they could go and attack the alcohol, giving us an E2 reaction, which is not what we want. We want an E2 reaction, or E1. And so the next step that happens here is that we lose the water molecule to generate a cation. And then another molecule of water, which now acts not as a leaving group like it did in the first step, but as a base, can abstract the neighboring proton to give us a final product, which will be an alkene. And as I said, all these steps are reversible. Okay, and this alkene will come with elimination of acid. Okay. So this is an interesting thing, that here water acts as a leaving group, but immediately the next step acts as a base. And as you know, water is a weak base, so this would mechanistically be an E1 reaction, which means that this follows the order of reactivity of tertiary alcohols are better than secondary, and these are significantly better than primary, but all of them will work provided that the conditions are forcing enough. This is an industrial reaction. They often run at very high temperatures to assure the complete conversion. Since this is an E1 reaction, things that we've already seen applying for E1 reactions apply here as well. So Zeitz's rule applies for getting the more substituted alkene, and then also these reactions are subject to rearrangements before finally the hydrogen is eliminated. To give you just one example, if we start with a very simple alcohol, cyclohexanol, treatment of this with H2SO4 at temperature of 140 degrees centigrade. You'll notice that this is significantly higher than the boiling point of the water. So the water boils off and it's removed from the reaction. And this will give us cyclohexene in a relatively high yield of 87%, which is synthetically very good. And again, to summarize this up, Alcohols are used often. Mechanistically, reaction is not much different from the eliminations of halides. However, what is different is that alcohols are very readily available. They're cheap compounds which are produced in huge amounts, and so this is economically a very worthwhile reaction when you want to produce an alkene. In the next subtopic, we will see how are alkenes produced on industrial scale. Industrial scale is subject to different set of conditions than lab scales, and we'll see how they play out.